for having provided this wonderful platform for us to interact in different paths by means of examinations, by means of live lectures by highly experienced teachers, expert question paper settings, and we have got doubt clarification platform, and hereafter in the live class also we would like to discuss some challenging questions posted by the students. You also become a part of it, and if you have any enthusiastic friends, let them also ask you to give some nice questions, so that we are there to answer your doubts, whatever it is. So coming to this particular second session in the solid state chemistry, the next session, as I promised you, today we will discuss various crystal systems. I think if you remember the previous session, we discussed about 4 varieties of crystalline substances: metallic crystals, where the points are occupied by metal ions; ionic substances, where the crystal points are occupied by ions, oppositely charged ions; and atomic crystals, like what we call network solids, covalent solids. The particles are simply the atoms connected through covalent bonds, and in molecular solids, crystals, we will have the places occupied by the molecules held together by van der Waals forces or hydrogen bonding or dipolar interactions, whatever may be the case. Before going into the bulk of the subject, we need to spend some time to understand some beautiful definitions which we always come across in solid state chemistry. You should always keep those definitions in mind while dealing with problems or some theoretical aspects of solid state chemistry. The definitions are: the first word is space lattice. Space lattice. Space lattice means the 3-dimensional arrangement of the particles. See, whenever I use the word particles, try to remember whatever is the repeating chemical unit in the crystal is called, I keep on referring as particle. The particle may be an atom, a molecule, or any ion, or whatever it may be. Solid is a 3-dimensional entity. So there the particles are nicely arranged following a systematic pattern. That pattern is called space lattice. For example, you may have some circles, these are all particles. See how they are arranged. They are following a systematic pattern, but be clear. I have just drawn the systematic pattern on the board in a 2-dimensional manner, but in real solid it happens in a 3-dimensional manner, and that arrangement is called space lattice. The word space lattice is it should give you a huge vision, the overall crystals arrangement. That is a space lattice. Lattice means arrangement. You always keep it in mind. So let us understand the second definition. Unit cell. This is the most wonderful word what we always come across in chemistry, solid state chemistry. Unit cell. Suppose you take a wall. Wall is made up of bricks. That brick is called unit cell. In a wall, how the brick repeats? A brick will be above a brick, below a brick, on the either sides you have bricks, just like that. A lattice is made up of a space lattice is made up of bricks. The minimum unit, the smallest part which repeats in all the directions, is called the unit cell. It is just not enough if you say it repeats in all directions. By seeing the unit cell, you should be able to explain the entire crystal structure. In other words, unit cell is a representative of a lattice. Unit cell structure is a presentation of the structure of the entire crystal. So, the entire crystal is explained simply if you can explain the unit cell. So, that is the minimum unit which represents the entire solid. So, if you want to study the whole properties of the solid, if you just study the unit cell is enough. So, you can say unit cell is the constituent which repeats in all directions. The unit cell is made up of some constituent particles of the chemical substance, solid, crystal. While selecting the unit cell, you should take a nice care that unit cell immediately should repeat above, below, on all sides. Same type of brick should repeat, and it should explain the entire structure. These 2 points you should remember. For example, if you take this particular pattern which I have drawn, what could be the unit cell? Just select this part. This part is representing the entire crystal. See, immediately the same part repeated. At the bottom also same part is repeated. See, each one is a unit cell. Remember, I am drawing it on the board, but it happens in all the 3 dimensions. So, that repeating unit is called a unit cell. You study the unit cell enough. The third word, what you should understand, the coordination number. Coordination number. This is, suppose there is an atom, around it in the space how many atoms are present or particles are present. There are many present, but the nearest neighbors around in the space lattice, if you take the entire space lattice, every atom or every particle is surrounded by certain number of particles. The closest particles number, the number of the nearest neighbors, is called the coordination number of that particular particle. Just I will explain. You select this, for example, you select this particle. How many nearest neighboring other circles are present? 1, 2, 3, 4. With reference to this circle, the other circles are 4. You can say the coordination number of this is 4 in one way. How many dots are present? With reference to these dots also, it is 4. To understand the coordination number better, I will give you 2 small beautiful examples. You see this pattern. This is a 2-dimensional pattern. I will select one of the particles, 2-dimensional way, on the board only. How many nearest neighbors are there around the shaded particle? See, this is surrounded by 1, 2, 3, 4, 5, 6 like this. 8 particles are there around it, but there is a smart word in the coordination number, the number of nearest neighbors. See, this and this are with x and x distance, but there are 4 other atoms with different distance. See, they are diagonally attached, I mean nearest, they are y distance, they are at y and y. X is definitely less than y, simple Pythagoras theorem. So, who are the nearest circles around that central circle? 1, 2, 3, 4. So, coordination number is 4. I will draw one more pattern, you will appreciate the coordination number in a better way. If this is a 2-dimensional lattice, what is the coordination number of each circle? I will select this. Who are the nearest neighbors? All the 6 are the nearest neighbors. This hexagon, see all the 6, 1, 2, 3, 4, 5, 6. So, coordination number is 6. And you will find the same thing throughout the lattice, 2-dimensional lattice. Sometimes we will come across ionic solids. Suppose you have got A plus B minus, A plus B minus, like this. In this case, the coordination number means somewhat a bit different. If all are identical, we will simply think of the nearest neighbors, number of nearest neighbors. But once it is an ionic compound like this, right now I am showing it, I repeatedly tell, on the 2-dimensional plane. In the animation version, I will show the 3-dimensional diagrams. We will select A plus. If you want the coordination number of a particular cation, you have to think of the nearest neighboring opposite ions. Who are the anions around A plus? A plus is a cation. Even though you have got so many B minus around, you have to select the nearest neighbors. So, this B minus, this B minus, this B minus, this B minus are the nearest neighbors. So, the coordination number of A plus is 4. So, simply what you will understand, when all are identical, like suppose you take iron crystal, there cannot be any other element other than iron atoms. So, in the systematic arrangement of iron ions in the iron lattice, around each iron ion, how many nearest neighboring irons are there? That number is called coordination number. If you take some magnesium oxide crystal, but that crystal will possess magnesium ions and oxide ions in systematic arrangement. So, around each magnesium, how many oxides are present in the nearest vicinity? Around each oxide, how many magnesiums are present in the nearest vicinity? If you want magnesium's coordination number, the number of nearest oxides. If you want oxides coordination number, the number of nearest magnesiums. The coordination number in ionic compounds would mean that. But if and only if something like this is asked, like how many magnesiums are there around each magnesium, that is a different calculation. How many oxides are there around how many oxides? The solid state gives you a lot of scope for number of questions and different methods of analysis of a crystal. So, first of all, this basic language you should understand before appreciating the crystal systems. So, the definite basic words what you should always be very clear with are, first one, space lattice, it is a 3-dimensional lattice arrangement. Second one, the unit cell. Unit cell is the least part of the crystal, the smallest part of the crystal, which you select, which repeats in all directions, forward, backward, top, bottom, left, right, which can explain the entire structure of the crystal. The study of the unit cell is nothing but the study of the crystal. That way you will have to think about new unit cell. The third word, the coordination number. According to situation, you will have to think about it. Of course, a crystal is made up of all identical particles. The number of nearest neighboring particles around a particular particle is the coordination number of that particle. I could show you only in the 2-dimensional manner. Whereas, in an ionic crystal, the number of nearest neighboring oppositely charged ions present is called the coordination number of that particular ion. So, remember these words, coordination number, unit cell and space lattice. Now, in the previous class, as I mentioned, there will be a natural limitation for the development of crystals of various substances. You can have ammonium bromide, copper sulphate, diamond, graphite, sodium chloride, lithium oxide, whatever may be, any solid you take, sugar, any crystalline solid you take, those solids must fall in their structure in one of the 7 varieties of crystal systems. There are 7 varieties of crystal systems based on the geometrical limitations, and in each crystal system again there can be some varieties of unit cells possible. I told you what is a unit cell now. I told there will be 7 crystal systems. In 7 crystal systems, if you select, in each crystal system there is some possible varieties of unit cells. That is also because of some geometrical restriction. You have got totally 14 varieties of unit cells defined by Bravais. So, we call them Bravais lattices. I told you 7 crystal systems and 14 unit cells. Do not be carried away by a feeling that it is 7 into 2, 14. It is not like that. Some crystal systems may have only 2 unit cells. Some crystal systems may have only one variety of unit cells. Some crystal systems may have 4 unit cells, but all put together you have 7 varieties of crystal systems, you have 14 varieties of unit cells that fall in those crystal systems. So, before really going into the crystal systems, we still need to understand some more words, that also I will explain. Suppose someone asks you how many A's and how many B's are there in the unit cell. Obvious and simple answer will be what? 1, 2, 3, 4, 5 A's. There are 5 A's appearing, 1, 2, 3, 4, 5. Suppose I ask you what is the formula of this unit cell. A small student will simply count the atoms and tell. There are dots, 4 dots, dot means B. So 4 B's. So he may say A5 B4 is the formula of the unit cell. Actually this is a wrong thing. Why it goes wrong? Because simple logic, it is a 2-dimensional lattice I am telling, means it is after all one unit cell, and it continues further like this, it continues like this, it continues like this, it will not come forward and backward because it is 2-dimensional. My simple question, is this circle completely belonging to this unit cell? No. The reason is, it is a part of the lattice, it is a continuum, you have to go like this also. Now see, if I select this atom is common to 4 unit cells. So for this unit cell, how much of this atom should be considered? That contributes only 1/4, because this atom is going into 4 unit cells. So you have to count only 1/4, here 1/4, here also 1/4, here also 1/4, because here also there is a continuation like this. What about this? This circle completely belongs to this unit cell. So effectively, how many circles this, I mean yes, this particular unit cell having 1/4, 1/4, 1/4, 1/4 will make 1. This circle is 1. So there are only 2 circles. How many B's are there? So this logic is very essential in solid state. This part, whatever is present on this line, is common for both unit cells. So you have to count only half of it. Similarly, this is also common for both unit cells, half of it. Similarly, this half. See half. How many halves? 1, 2, 3, 4 halves make 2. So this is B2. You got A5 and B4 in the earlier wrong assumption. You have to count like this. I can give a small real life example, like you have 2 houses, with one tree in between. Whose tree it is? The tree belongs to both the houses. There is one more house next to this, like that. How many trees this house has? It is sharing half of the tree here, it is sharing half of the tree with the next house. So effectively, this middle house is enjoying only one tree, and this kind of a logic we will have to use in many places in solid state chemistry, keeping in view the contribution of the particles to a particular unit cell. To make you understand still better, I will take a 3-dimensional lattice. What are you seeing there? One sphere at the center of a cube. I assume this cube is a unit cell. Now, this particular atom or molecule or ion, whatever may be the case, the sphere totally belongs to this unit cell. So, its contribution to this unit cell is 1. Whenever you have a sphere at the middle of a unit cell, there is a beautiful name for it, body centered position. If at all an atom or a molecule or a particle present at the center of a unit cell, we call such position as body centered position. I will show all this later again. Let me finish my logic first, you try to catch up. A body center atom completely belongs to one unit cell because it is not shared by more than one unit cell. Suppose I have an atom here. This atom is not completely belonging to this unit cell because this face is common for two unit cells. There is, think in the terms of lattice. So, go for the next unit cell. Now, you see, how many unit cells are you seeing? 2 unit cells. Each unit cell has a body center atom, keep it there, no problem, but the face is being shared by 2 unit cells. So, my simple question, this sphere, is it completely belonging to this unit cell? No, only half you should count because this is common for 2 unit cells, therefore, per unit cell only half you should send. So, whenever you see a face centered atom, there is a beautiful word for this also called face center atom, face centered sphere, face centered molecule, face centered ion, face centered particle. You should count only half. Suppose I take something here. Where is it present? It is present on the edge of a unit cell. How much should you count for this particular unit cell? You should check the edge is common for how many unit cells. I develop the lattice. So, now you see. The edge atom is common for how many unit cells? 1, 2, 3, 4. How much of this goes to this unit cell? Only 1/4. So, whenever you see an edge center atom, you count only 1/4 for the unit cell. Now, coming to, suppose I take one corner atom. How much of this goes to this unit cell? This is present in the corner. Let me develop the lattice. Now, I am thinking about this particle. See, the blue one is body center atom, the red one face center atom. The yellow one edge center atom, the green one corner center atom. I think you are not able to see this well. I will make this with a different color. Or I will do like this. Now this is common for how many unit cells? I will extend the units, suppose 1, 2, 3, 4, this is common, and do not be confined here only, come forward, before this 1 unit cell, before this 1 unit cell, before this 1 unit cell, before this 1 unit cell. So these are 4, at the front you have 4, for all the 8 unit cells this is common, therefore only 1/8 you have to consider for this unit cell. So in solid state, whenever you come across such cubes and all, the body center contribution should be 1 per unit cell, face center atom contributes half, edge center contributes 1/4, corner atom contributes 1/8 to the unit cell. This also you should keep in mind. Now let me give you a better idea. So whenever you see a unit cell, this is called body center, its contribution is 1 per unit cell. This is called face center, its contribution is half per unit cell. This is called edge center, its contribution is 1/4 per unit cell. This is called corner atom, its contribution is 1/8 per unit cell. So this you should always keep in mind. Now let me tell you, unit cells have some types. Suppose, after all, what are unit cells? A part of a crystal. A crystal contains particles. So unit cell also contains particles. Basing on the relative positions of the particles, we have got the unit cells divided into 4 varieties: primitive, body centered, face centered and end centered. Suppose I take a unit cell, 3-dimensional unit cell. If only corners are occupied, this is called primitive. If only atoms are present at the corners of unit cell, we call it primitive unit cell. Suppose you have got at corners as well as body center. If only corners are occupied, we call them primitive. Other corners is a must. Other than that, if you have one sphere at the body center, we call it body centered. If you have spheres in the corners and all the faces, corners and top face, bottom face, left face, right face, back face, front face. See what are you seeing there? Every corner has an atom. On the top face center you have an atom. At the bottom face you have an atom. See, top face, bottom face, left face, right face, back face, front face. See, all the faces are having atoms. In the corners you have got atoms, and that is called face centered cubic. Face centered unit cell, only corners primitive, corners and body, body centered, corners and all the faces, face centered. Other than this, you have got one more variety, end centered, end centered. Suppose you have got some unit cell like this. Don't worry about lengths and breadths, heights and all. Placement of spheres. I have got definitely all the corners filled. All the corners filled. Now, how many faces are you seeing there? 6 faces. But only one of the opposite, one set of opposite faces is filled with at the center with sphere. See the difference between face centered and end centered. This is end centered. In face centered unit cell, at the center of every face you will have a contributing particle. In the end centered unit cell, only one pair of opposite faces will have particles or whatever contributing molecule, particle, sphere, whatever you call. So, how many varieties of unit cells are there? 4 varieties. These 4 varieties may not be present in all the crystal systems. I have been insisting on one point, all the crystalline solids must fall in any of 7 varieties of crystal systems. I will define them. In those crystal systems, there can be some varieties of unit cells possible. I said possible. Possible means what? There will be some geometrical limitations, based on that only few varieties of unit cells are possible out of this. See, all the 4 varieties may not be possible in all the 7 varieties of crystal systems. Some variety of crystal system, one type of crystal system may have one variety of unit cells, or 2, 3 may be there, 4 may be there. So, like that we will have to understand. So, once you know this language, it is very easy to understand those crystal systems. Now, on what basis the crystal systems are defined? As I told you, Bravais lattices are defined on the basis of the geometrical limitations in terms of length, height, breadth or depth parameters, means distance parameters in the space lattice. In the space lattice, the particles are nicely arranged in the 3-dimensional space, and you can cut planes in the particles, planes of the particles. Among those planes, we will have parallel sets of planes. Excuse me. The distances between the planes, angles between the planes, we will consider. Based on distance parameters and angle parameters, the 7 crystal systems are defined. The 7 restricted, geometrically limited crystal systems are defined on the basis of distance parameters and angle parameters between the planes, adjacent planes. That we will think now. To understand crystal systems, first we will go with unit cell. So, just now I told you what is a unit cell. See, this is space lattice, complete lattice, 3-dimensional arrangement. If I speak that first, you will understand this nicely. What did you observe there? There is a small part cut, that is called unit cell. And is that only part? It is repeating backward, left side, top, bottom. And that unit cell is drawn here, you see. The height of the unit cell C, depth of the unit cell A, width of the unit cell B. See, this is B, the height is C, this is A. See the angles, alpha, beta and gamma. So, you can take like this, length is A, B, C, angle between this alpha, angle between this beta, angle between this gamma. How are they angled? Based on those parameters only we have got 7 varieties of crystal systems. And I think now it is very clear for you. Space lattice means a huge arrangement in 3-dimensional manner. Unit cell is a small part, small repeating part, and within unit cell you have got these parameters. Based on these parameters we have got 7 varieties of crystal systems. See, you can see now the unit cell, everywhere you will find so many unit cells, not only a single unit cell. You have got pretty good number of unit cells depending on the bulk of the total lattice. See, that unit cell can go any direction. Coming to this, that is space lattice, showing you a clear view of unit cell. See this, there are 3 angles, alpha, beta, gamma and 3 lengths, the height of the unit cell, the depth of the unit cell and the width of the unit cell. So, you have got 3 distance parameters A, B, C, and there are 3 angle parameters. So, based on this we have got some crystal systems. Just now I discussed unit cells are of, basically we say 2 varieties in the sense of a broader view. If you have only corners occupied by the atoms, particles, we call such unit cell as a primitive unit cell. Some unit cells are centered. Centered means what? Other than the primitive, means other than the corners, some other places are also occupied. If you just see this everywhere, what about this? The face centered. Just now I showed you in my previous explanation. See, in this you have got every corner occupied and every face occupied. Corners occupied and central face center atoms are also present. Such unit cell is called face centered unit cell. What about this? What are you seeing here? Every corner is occupied and at the center you have a atom. Other than the corners, at the middle of the unit cell there is an atom, there is a particle. What did I define that? I drew 4 varieties of unit cells in my 15 minutes ago lecture. If at all the corners and the body centered position are occupied, we call it body centered unit cell. Body centered unit cell. It may be in any system, that is a different story. Body centered. Now you can easily recognize that unit cell. Where do you have atoms in that unit cell? Just like primitive, you have all the corners occupied. All the corners occupied. but if you carefully observe, all the faces are not occupied, only you have got corners occupied, and top face there is a sphere, bottom face there is a sphere. What do we call it? End centered unit cell. See, 4 varieties of unit cells are possible. So, just conclusively I tell one thing: primitive will have corners occupied, face centered unit cells possess corners occupied, and all the faces, back face, front face, right, left, top and bottom, it is only a unit cell. Body centered unit cell, corners and the body center position occupied, end centered, corners and one set of opposite faces, that is called end centered. Now, let us switch over to the real important aspect, 7 crystal systems. See how it is, you can see. You can see the particles at the corners. See, you can see particles at the corners and face centered positions. So, we call it face centered. Just see, every face has got one particle. Here, see corners and the body center position. So, we call it a body centered unit cell. You observe the last one, you have only one set of opposite faces having the spheres. So, you can see that is called end centered unit cell. So, let us now switch over to our next slide. Table of crystal systems, I told you 7 crystal systems. On what basis the systems are defined? A, B, C relation, length parameters, alpha, beta, gamma, angle parameters. So, based on that we have got 7 varieties of crystal systems. Crystal system, type of crystal systems, I mean name, the distance parameter, angle parameter, possible variations means what? What do you mean by possible variations? I clearly mentioned in every crystal system there need not be the same number of unit cells possible, there will be geometrical restrictions. There are 7 crystal systems, there are 14 varieties of unit cells, but it is not 7 into 2 14. Some systems may have more unit cells possible, some systems may have less unit cells possible in them in the crystal world. Let us now see most popular variety of crystal system, the cubic crystal system. Cubic means what? All the 3 lengths are identical. You have length of the unit cell, breadth of the unit cell and height of the unit cell, all are same. Simply you will get a cube. The unit cell is simply a cube. What about the angles between the planes, adjacent planes? Alpha is equal to beta is equal to gamma is equal to 90 degrees. So, how can you visualize that? We will see now. In this variety of crystal system, be careful, the language is very essential. It is a crystal system. Which crystal system? Cubic crystal system. In cubic crystal system, how many varieties of unit cells may be possible? How many Bravais cells? Primitive is possible, body center is possible, face center is possible. which is not possible in cubic system. End centered is not possible. So, how many unit cells are possible in this system? 3. If you see the entire world of crystals, many crystals are there in universe. You select any crystal, if at all that crystal follows cubic system, A is equal to B is equal to C, alpha is equal to beta is equal to gamma, which is also equal to 90 degrees, in that particular system you cannot find an end centered unit cell. You will find only primitive. Student must remember this. How many varieties of unit cells are possible in cubic crystal system? These parameters are satisfied. There can be only 3 varieties of unit cells possible. Do not forget their definitions. Primitive means only corners occupied. Body center means corners and body position. Face centered, corners and face position occupied. Like this, how many will I show you? 7 systems. I will show you 7 systems. In each system there are certain number of possible unit cells, that you should remember. For each system, what are the parameters? See the name, tetragonal unit cell, tetragonal crystal system. This column is for crystal system, tetragonal crystal system. How is it defined? A is equal to B, but C is not equal. It means it may be something like this, A and B are same, but C is not same. So, this A and this B are same, but height is not same. Also, what is he telling? Alpha is equal to beta is equal to gamma is equal to 90. All the angles are 90 only. So, this is how you have got tetragonal system. In the tetragonal system, you have got only 2 possible unit cells. What are they? Primitive unit cell and body centered unit cell. In this system, you can't have face centered, you can't have end centered. You will only have that limitation is there in nature. So, in this, so how many unit cells? The previous there are 3, the present 2. In the primitive and body centered are possible in tetragonal crystal system. And the third variety of crystal system is orthorhombic crystal system. This name is based on these parameters. How is this? A is different, B is different, C is different. If you select a unit cell in the orthorhombic system, the length of the unit cell, breadth of the unit cell and the height of the unit cell will not be same. They will be different. Now, what about the angles? Alpha, beta, gamma are equal to 90. So, I think in the older days you can see matchboxes. A matchbox, length is different, height is different, breadth is different. So, A is not equal to B is not equal to C. So, it is almost like this. See, the height is A, depth is B, length is C. They are not same, but angles are same, 90 degrees. Matchbox, it is orthorhombic system. And the beauty of orthorhombic system is, in this particular system you can see all varieties of unit cells. We have defined 4 varieties of unit cells at the maximum. So, you have got primitive, body centered, face centered, end centered. Maximum all unit cells will be possible. In which crystal system? Orthorhombic crystal system. You have got 4 varieties possible. Keep it in mind, there should be 14 varieties of unit cells in the 7 varieties of crystal systems, and the golden rule is The 14 is not 7 into 2, not like that. Some systems have 3, your cubic system has got 3 unit cells, tetragonal has got only 2, orthorhombic has got 4, yeah. What is my fourth unit cell? Fourth system, monoclinic system. What are its parameters? None of the length is equal, not even a single length is equal, monoclinic. Length is different, breadth is different, height is different. That is there even in orthorhombic. These two are same in this aspect. But how do they differ? In orthorhombic, see, all the angles are 90, but in monoclinic 2 angles are 90, one angle is not 90. So, one of the planes may bend. If you take a matchbox and keep a big stone on it, it will bend like this. So, one of the angles just bends, it will not be 90. 2 angles are 90, one angle. How monoclinic and orthorhombic differ? In monoclinic and orthorhombic, the length, breadth, height are same. I am sorry, length, breadth and height are parameters, pattern is same. None of them are equal in both. The only thing, in orthorhombic all angles are 90, in monoclinic one of the angles is not 90. So, because of this feature, it has lost the chance of enjoying 2 varieties of unit cells. Orthorhombic can have primitive, body center, face center, end center, but what is this having? Only primitive, only end center is possible. You cannot have face centered and body centered. So, how many varieties of unit cells are possible? So many times these questions have come in competitive exams. See, they give this, ask this, or they may give cubic, ask these parameters. Sometimes they give parameters, ask possible number of unit cells. So, which system may have highest number of unit cells? See, from this table itself you can produce 6-7 questions. See, totally I said 7 unit cells, 7 crystal systems. We will switch over to the fifth, hexagonal crystal system. It is a crystal system. A is equal to B, 2 lengths are equal, one is not equal. But there is something very interesting here. 2 angles are 90 degrees, one angle is 120 degrees. You can go for it, actually we can draw. I think this gives you some beautiful thought. See the crystal system, you can see the lengths. See, this length are same, A and B, or I can say A and B are same, but height not same, somewhat longer. So, A is equal to B, but not C. In this you will have only primitive, actually we will select only till here, this is the unit cell. You can see this, see 2 lengths are same, one length is not same, 2 angles are 90, one angle is 120. So, that is the issue, and you can have only primitive unit cell in this particular hexagonal crystal system. Only one is possible. So, what is the next variety of crystal system? Rhombohedral. Rhombohedral. Again A is equal to B is equal to C, means what? Length, breadth and height are same. This condition is there even in cubic. So, what do you expect? Where do cubic system and rhombohedral system differ? Definitely in angles. In cubic you have got all the angles same. In rhombohedral, how the angles are present? Alpha, beta, gamma will be same but not 90. There is a beautiful difference between cubic and rhombohedral. In cubic, lengths are same, angles are same, angles are equal to 90 degrees. In rhombohedral, lengths are same, angles are same but not equal to 90 degrees, can be anything. How many unit cells are possible? Only one. So, let us switch out to the seventh crystal system, triclinic. See, here also A is not equal to B is not equal to C. In how many crystal systems you have this condition? A not equal to B not equal to C? Orthorhombic, monoclinic, triclinic. In all the three, A not equal to B not equal to C. In triclinic, even here the angles are same but not equal to 90. In triclinic, all the angles are different. Not even a single angle is 90 degrees. All the angles are not equal and also each one is not equal to 90. There also you will have only primitive. So, this is also having 1. So, totally how many unit cells are there? 3 are possible from cubic, 2 are possible from tetragonal, 4 are possible for orthorhombic, 2 are possible for monoclinic, 1 each are possible with hexagonal, rhombohedral and triclinic. So, put together if you add all this you will get 14. The 14 unit cells are called Bravais lattices, Bravais unit cells. So, I advise all the students to get this table by heart by means of the mutual relations between the length parameters A, B and C, angle parameters alpha, beta, gamma. Suppose someone in the examination gives A is equal to B is equal to C, alpha is equal to beta is equal to gamma. This is a crystal system. This system can form how many unit cells? By seeing A is equal to B is equal to C, alpha is equal to beta is equal to gamma 90, you should understand it is a cubic crystal system. In that cubic crystal system, how many unit cells are possible? 3 are possible. So, based on this table, there is ever possibility you may get a question in any competitive exam. Now, you just see Bravais lattices in cubic system. You have got 3 varieties, just now I showed. In cubic system you have 3. Face centered, body centered, end centered, primitive cubic system. Next one, tetragonal, you have got 2 unit cells, primitive, body centered. The third, orthorhombic system, you have got 4 varieties of unit cells, end centered, face centered, you got body centered, you got primitive. All the 4 varieties of unit cells are there. Monoclinic, you have 2 varieties, end centered, primitive. See, in hexagonal you have got only primitive possible, only primitive. Hexagonal system you have only primitive possible, you cut that piece. In that particular rhombohedral you have got how many unit cells? 2, only primitive, sorry, you have got this only possible, rhombohedral, only primitive it gives. The last one triclinic, primitive possible. So, with this I end today's lecture. We have really appreciated the most important fundamental language of solid state chemistry by means of space lattice, unit cell, coordination number, 7 varieties of crystal systems, contribution of particles in a unit cell, 7 varieties of crystal systems and number of unit cells in each crystal system, and we will try to now appreciate cubic system and hexagonal system that are present in your syllabus in our incoming future classes.